The problem of the SR latch, then S prime, R prime latch, and also SR latch with control input. So these three types of latches have an undefined state, and then the D latch does not have the undefined state. The symbol of a D latch is that D for data, and that's the control input. We have Q, we have Q prime. So now the primary objective of the control input is that by using this flag, we want to control the entire device. So when C equals 0, then no changes occur for this latch. It means that input never goes to the output. So the output will be unchanged forever as long as C is 0. When C is 1, then the input data goes to the output port, and the device works as a D latch. So now if we want to control this device by using an input pulse, something like, let's consider this is the pulse that we apply in the control input. So when this pulse is 0, so then the device is inactive, the device is not triggered. So when the pulse is 1, the device is triggered. Again 0, no triggered, 1. So now my question is, so how many times the device is triggered? So when the pulse is 1, so in a single cycle, so let's consider the cycle from here to there. In a single cycle, so here there are infinite number of points. So it is possible that the device is triggered infinite number of times, something that we do not want. So we want that for every cycle the device is triggered just once. So in order to doing so, we try to build another device which is triggered when the pulse goes from 1 to 0 or 0 to 1. So 1 to 0, so it goes to 1 to 0 or 0 to 1, and those devices we call flip-flop. So a number of types of flip-flops such as JK flip-flop, then we have T flip-flop, D flip-flop. So particularly in this class we'll study this D flip-flop. Flip-flops are of two types. So when the flip-flop is still triggered for the pulse, so when it goes to 1 to 0, then this flip-flop we call is a negative edge triggered. So when the flip-flop is triggered, so for 0 to 1, then we call is positive edge triggered. Positive edge triggered flip-flops. So now let's start first with the negative edge triggered D flip-flop. So D flip-flop, D for data. So now, so in order to doing so, we need a D latch and we need a SL latch. So we have a D latch. We also have a SR latch. It's the D latch. It's the control. It's the SR latch. The control. We have Q prime. We have Q prime, and these are connected. And we have a control signal here, and the opposite or the complement of the control signal, if the control is 0, then the complement is 1. If the control is 1, it is 0, the complement is 0. This is added to the control input of the second latch. Now we have that D, Q, and that's the C for control. So there are two latches in this case. The one latch is the master latch, and the another latch is the slave latch, and this is also called a master slave flip-flop. We want to see the functionality of this flip-flop. So what actually happens here? So for different regions of the clock pulse. Sorry. The clock pulse is of this type. So when the clock pulse is 0, let's consider this part or that part or that part. So the clock pulse can be 0. So what happens? If the clock pulse is 0, then the first flip-flop is not triggered, but the control input of the second flip-flop, the second latch, is 1, so the second latch is triggered. The first flip-flop is not triggered. It means that the first latch is inactive, and the second latch is active. So what happens? That this input D does not go to the output of the first latch. So then this D will never go to the output of the entire flip-flop. So this means that no changes occur. So no changes occur. So when the control is 1, then what happens? Then the first latch is triggered or becomes effective, but the control input of the second latch is 0, so that's not triggered. So D will go there at the output of the first latch, but since the second latch is not triggered, this will not go to the output of the second latch. So still no changes occur. Now so when the clock pulse goes from 0 to 1, for the edge triggered parts, what happens? So this is going from 0 to 1. So when it is 0 initially, then the first flip-flop is not triggered. So D will not go to the outcome of the first latch. So we don't get the data here. We don't get the data at the output of the first latch. But the second latch is triggered because the control input of the second latch is 1. It comes by reversing the original control input. The original control input is 0, and the control input for the second latch is 1. So the second latch is triggered, but it actually does not pass the data from input to the output of the entire device, because the data is not going through the first latch. So suddenly when the clock pulse or the control input changes from 0 to 1, then what happens? So as soon as it changes to 1, then the first flip-flop gets triggered and the second flip-flop is not triggered. So D will go to the output of the first latch but not to the output of the entire device. So in this case also no changes occur. Now so the another case, when the clock pulse goes from 1 to 0, what happens? So we have it 1, the control input is 1, the first latch is triggered, so data goes to the output of the first latch, so we get D in the output of the first latch. Then as soon as the control input goes to 0, then the first flip-flop becomes inactive, but the second flip-flop becomes active because the control input of the second flip-flop is 1. So then this data D will go to Q. So this is actually change. It's change. So we get D here. It's changing. So if D is 0, then we get, if D is 0, then we get 0 there. If D is 1, we get 0 1. If input is 0, output is 0. If input is 1, output is 1. So this based on the C. So if we say C is the control, by using this C, we actually can control the entire device. So in every cases it's not triggered, the device is not triggered, but when the clock pulse or the control input goes from 1 to 0, then the input goes to the output. The symbol for this flip-flop is that, so it's a D type flip-flop. See, we have Q, we have Q prime, and now that is the clock pulse, is a flip-flop, and also is a negative edge triggered flip-flop, and the negative edge triggered flip-flop is also denoted by that symbol because it gets triggered when the clock pulse goes from 1 to 0. Now we want to study the positive edge triggered D flip-flop. Now, so we got the negative edge triggered D flip-flops. In order to make a positive edge triggered D flip-flop, we just need to add another inverter. So we got the same circuit again. So we have the D latch, we have C, we have Q prime, S, R, Q prime. So this is the negative edge triggered D flip-flop. So now what we want, so we want to add an additional inverter or a NOT gate here. Then after analyzing this device, we will see that this actually gives us a negative, a positive edge triggered D flip-flop. Let's analyze this circuit. So we have C and we want to find the output Q. So when C is 0, what happens? When C is 1, what happens? When C is 0 to 1, what happens? When C is 1 to 0, so what happens? So C is the clock pulse. We know that it's a C. It's a clock pulse. Now, when C is 0, then C is 0. It's 0 here. Then we get 1 there. So the first latch is triggered. Then D goes from input to the output of the first latch, but the second latch is not triggered. So D does not go to the output of the entire device. So there is no change. When C is 1, then the first flip-flop is not triggered. The second latch is triggered. So D goes to the output of the first latch, but not to the output of the second latch. So still there is no change. When the control input goes from 0 to 1, so when it is 0, the first latch is triggered. So D goes there at the output of the first latch. Then as soon as it becomes 1, the second latch is also triggered. So D goes to the output of the second latch. So we actually get D. So for this combination, if D is 0, then Q is 0. If D is 1, then Q is 1. It means that Q equals D. Q and D are the same. And for the very last combination, when it goes to 1 to 0, when it is 1, the first latch is not triggered. So D doesn't go to the output of the first latch. The second latch is triggered, but doesn't matter. So the first latch is not triggered, so it's actually breaking the circuit. So when it is 0, the first latch is triggered, but the second latch is not triggered. So there will be no changes again. The symbol for this flip-flop is a positive edge triggered. So the difference between the negative edge triggered and positive edge triggered will be that the clock pulse. Okay, so now we have this positive edge triggered. So but we don't have the little bubble that we had in the case of negative edge triggered flip-flop. It's also denoted as this symbol, because it indicates that this flip-flop is triggered when it goes to 0 to 1. Now we study how to design sequential logic circuits. So sequential circuit design. As we saw that for the combinational circuits we have truth table, but for sequential circuits we will have state tables. State table has input, has current state, it has output, it has next state. So this input and output, this part is also in the combinational circuits, but the current state and the next state, these two are new. And every state table can also be represented graphically, and that graphical representation we call state diagram. State table and state diagram contain the same information, but just two different representations. Sometimes the state diagrams is easier to follow because this is in graphical form. We want to see this state table and state diagram by using an example. Okay, let's we have a state table, like we have one input I, then we have two flip-flops Q1 T, Q2T is the present state, and then so we have output O, one output, and the next state q1 t plus 1, q2 t plus 1. So we'll have a total of 8 combinations. Zero 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 1 1 0 1 1 0 0 0 1 1 0 1 1. And on the other side we have 0 1 1 1 0 0 0 0. Then we have that 0 0 0 0 0 1 1 1. We have that 0 0 0 0 1 1 0 0. Well, so this is the state table, and we want to find the state diagram. So since there are two flip-flops here, so q1 and q2, so by using the two Boolean variables, we can have 4 combinations, and these combinations are 0 0 0 1 1 0 1 1. Okay, and each of the combination is a state. So now so for the first row in the state table, we have that the present state is 0 0, the next state is also 0 0. So this actually from 0 0 to 0 0, input is 0, output is also 0. For the second one, the state transition is from 0 1 to 0 0, 0 1 to 0 0. Input is 0 and output is 1. For the third row, the state is 1 0 and the next state will be 0 0. So that's 1 0 to 0 0. Input is 0 and the output is 1. Now for the next row, the present state is 1 1, next state is 0 0. So it goes from 1 1 to 0 0. Input is 0 and output is 1. We're done with the 4 combinations. The fifth combination is the state transition is from 0 0 to 0 1. So that's 0 0 to 0 1. Here you go. And input is 1, output is 0. Then we got 0 1 to 1 1. 0 1 to 1 1. Input is 1, output is 0. Then we got 1 0 to 1 0. Okay, so it's no change. 1 0 to 1 0. Input is 1, output is 0. Then the very last combination 1 1 to 1 0. So that's 1 1 to 1 0. The input is 1 and output is 0. So that's the corresponding state diagram of the state table. So if we are given a state table, then we can find the state diagram. Similarly, if we are given a state diagram, from the state diagram we can also find the state table. So in order to finding the state table, we need to identify the input, output, the current state and the next state, and we need to consider each of the combination of input and current state. Then we need to find the corresponding output and the next state. Now, so given this state table, so if we want to design the circuit, the sequential circuit, so we need to find the equation for each of the output and for each of the flip-flops of the next state. So we have one output in this case and the two flip-flops Q1 and Q2. So the if we consider we have 3 binary variables I, Q1t and Q2t, I, Q1t, Q2t. Then we have the output O. then by using a 3-variable K-map, we can find the function for O in terms of I, Q1t and Q2t. Similarly, we can find the function for Q1t plus 1 in terms of I, Q1t and Q2t. Again, we can find the function for Q2t plus 1 in terms of I, Q1t and Q2t. I'm not going to go detail in the K-map. So, but if you do so, then what you will get, I'm going to write the equations directly. So we'll get O, then we'll get Q1 t plus 1, we'll get Q2 t plus 1. This 3 equations. For O, we'll get I prime Q1t plus Q2t. I'm not showing them. These are easier to find by using K-map. And for Q1 t plus 1, we have I Q1t plus Q2t. For Q2, we have I Q1t prime. Okay, so now given these 3 equations, so we want to draw the circuit. Definitely, so we need 2 flip-flops, and let's consider them. The first flip-flop and the second flip-flop. Each of the flip-flop is D-type. Positive edge triggered or negative edge triggered doesn't matter. This D, and the clock pulse also positive or negative. So let's consider the negative. That's the clock pulse, and we have Q there, Q prime, Q prime. So the first flip-flop, let's consider this is our Q1, and the second flip-flop is our Q2. Now, so what do we get? So we get Qt, we get Qt plus 1, Q1t actually, Q2t, Q2t plus 1. And then we have input here I and output there O. So, and let's find the circuit for O first, the output. So O equals I prime. Okay, we need I prime. So we need an inverter here. It will give us I prime. Then we need an OR gate between Q1t and Q2t. Q1t and Q2t, and we need an AND gate, and that is the O, the equation, the circuit for O. Now let's find the circuit for Q1 t plus 1. So what do we have? What we need? So we need I. We already got I. Then we need Q1t plus Q2t. So we already got that here. So we need an AND gate. Let's consider the AND gate here. The one input is I. Is getting a little complicated because of the space, but the circuit itself is not that complicated. Okay, there's I, and we also have Q1t plus Q2t. There we go. Okay, so then this is Q1t plus 1. Now, so we need to find the q2t plus 1. We have I and we have q1. So we should have I and we also have q1 t prime. So I and we need an AND gate. We need an AND gate. The first input of the AND gate is I. Okay, so do we have I there? We have I. From here we can take this I. The second input is q1t. So we have q1 here, the q1. So this one is definitely q1t. So now we don't need to make q1 prime t, because q1 prime t is already here. So we are going to take this one and as an input to the AND gate, and the output of the AND gate will be q2 t plus 1. So we got, in this case, we got the input I, we got output O. So we got the present states here, q1t, q2t, and we also get next state there, q1t plus 1, q2t plus 1. Let's consider another example. So we have a state table and it has two inputs, I0, I1, and one flip-flop, Q1, or simply Q. So since we have only one flip-flop, we don't need Q1, Q2, or simply Q, or Q1 is also okay. I don't mind about that. And we have one output and also definitely the next state. Now, so we need to consider the 8 combinations. We are actually given these 8 combinations. The state table is given and we would like to design the sequential circuit. Okay, so and we know how to find the state diagram from a state table. So we have single flip-flop in this case. So there might be two states, 0 and 1. Okay, let's consider the first state 0, the second state 1. So finding the state diagram for designing a circuit is not a requirement, but so in exam it's possible that I can give you a state table or a state diagram for designing a circuit. So if I give you the state table, then so you find the equations and draw the circuit. And in order to finding the equations, you need to use the K-map. Or if you use other tools, I'm also fine with that. But on the other side, if I give you a state diagram, then probably it's better to find the state table first from the state diagram, then designing the circuit. Okay, so in this case, for the first row, we have the state from 0 to 0. Okay, 0 to 0. Input is 0, 0, and output is 0. For the second one, we have 0, 1 to we have 1 to 1. So we have 1 to 1. Input is 0, 0, and output is 1. Then we have 0 to 1, the state transition. Input is 0, 1, output is 0. Then we have 1 to 0. Input 0, 1, and output is 1. Then we have 0 to 1. So it's 0 to 1. Input is 1 0, output is 0. We have 1 to 0. Input is 1 0, output is 1. Then we have 0 to 0. 1 input and 0 is output. Then we have 1 to 1, and no state changes. So 1 input and 1 output. That's the state diagram. So now, in order to design the circuit, we need to find two functions, the functions for O and the functions for Q, T plus 1. We don't need that. We don't need the state diagram. So we need to find the K-map. Then we need to find two functions. So we need a 3-variable K-map. For O, we have I0, we have I1, we have Q, T plus 1. Then for O, 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1. Okay, that is easy. So then the function is Q T. Qt is the function. It's easy. Now, so for the second one, I0, I1, Q, T plus 1, 0 1 0 0 0 1 1 1 1 0. Now we have 0 1 1 0 0 1 1 0 1 0 0 1. Okay, so now we can take this one individually, that one individually. Then we'll see that the terms that we get from this one and from that one, that term involve I0. So we can take I0 separately, and then similarly the terms that we get from that one and from the other one, we'll get I0 prime. That's how. So after simplifying this equation, so what we'll get here, ut plus 1 equals I0 exclusive or I1. We can put a bracket or not, either way it's okay. Then Q T. This is something similar that we saw in the case of full adder circuits, or the full adder circuits. Yeah. And so this is QT, not QT plus 1. Also, we got these two equations, and we want to draw the circuit. We need space. So we need one flip-flop. So for Q only, is D, is Q, and is the clock pulse. Let's consider negative edge triggered flip-flop, and this Q prime. That's the flip-flop, and you can observe that. So I'm actually drawing the flip-flop in reverse way. In the right hand side I put D, in the left hand side I put Q. Is for drawing convenience, but if you do it other way, that is also fine. So we have two inputs, I0 and I1, and we have one output O, and let's find it for output first. So that's QT, and that's Q T plus 1. So now O equals QT. So this is very straightforward. This will directly go to O. O equals QT. And for QT plus 1, so we need an exclusive OR gate. then another exclusive OR gate, and that will be QT, and this will go to QT plus 1, and that's it. That's a simple circuit. So we got the inputs, we got the output, and we get the present stage here, and then we get the next stage there. Thank you.